following lecture, you have Pospíšilík. It's just Pospíšilík.
Ten laser to červené, že? Jo.
So, good morning. Let me introduce myself. I am Václav Pospíšilík, and my topic is issue of heat mirror films overheating. So, I will talk about heat mirror films. What is it? What does it mean? And so on. Benefits and so on. For the first, and after that, I will show how I determine optical properties of coated and uncoated glasses and polymer films. It was performed spectroscopic measurement by me and my colleague from Nanotechnology Center. So I will show you that. So after that, searching for measure absorption band of polymer films. And I will talk about evaluation of surface temperature under given conditions. On the end of presentation, I will make a comparison of several types of glazing. So how does it look like? So you can see on the picture three heat mirror insulating glasses. So the first wall, the outside surfaces is made of glass, and inside the space is polymer films. The polymer films can be coated or uncoated. The coated polymer films, it does mean that it has a silver layer, thin silver layer, and the name of coated polymer films is heat mirror films. So the problem of heat mirror films is that it overheats, and that is my task. What I analyzed. So as I mentioned, this is a cross section of glazing. The polymer film is stretched inside the interglazing space, and the space between glass and film is filled with argon or krypton with inert gas. This film divides a big space into two smaller, and this is important because we try to avoid natural convection. Okay, I performed, and with my colleague, spectroscopic measurement with this spectrophotometer, as you can see on the picture, in the spectral range from 250 nanometers to 2000 nanometers, and we determined reflectance and transmittance, and absorbance was calculated from this relation, as you can see below. So we determine optical properties from of films and of glasses. This is the first data from spectroscopic measurement. As you can see, the blue line is uncoated polymer films, and the orange line is coated polymer films. It is heat mirror films. The absorption band is larger and is shifted towards to longer wavelength, and this is the problem why heat mirror films is overheating, or heat mirror films overheat. It is also important to know optical properties of glasses, because they are in the glazing also included. For example, the blue line is a typical uncoated glass. As you can see, with the highest transmittance in the visible range and in the near infrared range, compared to, for example, red line. It is a coated glass with anti-solar protection, and it has only the highest transmittance in visible range. And it is important to say that the ultraviolet spectrum, ultraviolet radiation, is totally reflected or absorbed, and it is important for my next calculation. So I determine energy which was absorbed on the surfaces, the glass and on the glasses and plastic film. So as you can see, a solar radiation incident on the first glass and partially is reflected or absorbed or transmitted. The transmitted part of energy is again, part of energy is reflected, absorbed or transmitted. The contributions here is are absorption. This is a contribution of energy, or this is part of energy which was absorbed on the plastic film. And this is an infinite series, which can be rewritten into these relations. So this is absorbed energy at given wavelength. And when we integrate overall wavelength, we get total absorbed energy on the surfaces, on the surface. You can see that I consider only black body source. So I didn't consider atmosphere attenuation. So this is a little bit simplification, but not so significant. So initial conditions, solar radiation incident in perpendicular on the surface of glazing. So, and I consider that with intensity of radiation 1000 watt per square meter. For example, heat transfer coefficient, what I considered was given according to the standards. Width of the gas phase, that's mean width between gas and film is, I considered 12 millimeters. So now you can see a cross section of glazing with outside and inside conditions given by temperature and heat transfer coefficient. This is a temperature distribution with highest point in the polymer film and the heat mirror film on the polymer film. And this is heat output, input, sorry, this is a heat input on the polymer film. So this is a Q solar radiation, and this is heat output. The heat transfer is by radiation and conduction. Convection I didn't consider, but I calculated Nusselt number in this case, and the Nusselt number was 1, so I didn't consider convection term. This is energy balance equations. So the first term is energy absorbed. The two, these two are conduction terms, and these two are radiation terms. And because it is in equilibrium, thermal equilibrium, the sum of these contributions must equal to be to 0. This is the first. These are the first results. The maximum temperature can reach 65 degrees Celsius. So it's too high, and the polymer film or the heat mirror film can be deformed. And so this is a problem. This is a problem of overheating. The blue area is energy absorbed on the polymer film heat mirror 44. So the blue area is large, is too big in comparison of heat mirror classic, which is polymer film classic, which is uncoated film. So the area is very, very small compared to the first one. And this is the last slide. I do a comparison of the same heat mirror films but in the different glazing. The first glazing has the front glass, typical the front glass uncoated glass, flow 4. The second chart has or the second glazing, second concealed glazing has coated anti-solar with anti-solar protection layer, coated glass with anti-solar protection layer, and this glass eliminated ultraviolet fraction of energy, and the heat mirror films are not or heat mirror films don't overheat so much. So this is important to say. So it is suitable to combine glass, coated glass, with heat mirror films. So thank you for your attention.
Questions? Could you tell us what gases were in the gaps between the layers?
What gas?
Yes.
What gas? Argon. I considered argon, but it could be used, for example, krypton or xenon.
Yes.
Do you mean this question?
It means one atomic
gas, inert gas.
Yes.
Yeah.
So it doesn't radiate.
It has a low thermal conductivity, and this is important for thermal insulation properties of gases.
Yes. So no further questions. Thank you very much.
Thank you.